So this week we're going to look at sections 6.3 and 6.4. We're going to be splitting 6.3 up into several days. 6.4 we'll do in one day. But this week is all graph. Okay, so we're looking at what these graphs look like. So we've done a little bit numerically, but we're going to see like pictures of them. And we're going to focus mainly on sine and cosine. Okay, that'll be 3 of the days this week. The 4th day we'll look at all the other ones, but we don't go into as much depth in those. But sine and cosine we do quite a bit. The nice thing about sine and cosine is when we do transformations like shifting and stretching, everything is exactly the same as every shift and stretch we've done on it. Okay, that doesn't change. All right, does anybody know what sine or cosine looks like when you graph it? It's not linear. It's not a straight line. It's very different.
Just a little, I don't know how to describe it, a wave.
Yeah, it looks kind of like a wave. So let me graph both of them. Okay, so here's sine and cosine.
Isn't it where like sine is like one wave and then cosine is just the other wave?
Well, there is a connection between them.
Or no, never mind.
That's cosine in red. They're horizontal shifts of each other. So if you took the blue one, which is sine, and you shifted it left, you would get the red one. Or if you took the red one and shifted it right, you would get the blue one. Yeah.
So why do we have to differentiate between them?
Well, because there are different functions in math.
Okay.
So there's sine and cosine. You can use one in place of the other if you know how to do it, but sometimes it's easier to just use sine or cosine.
Okay.
But yeah, anything you can do with sine, you can do with cosine, and vice versa. So these kinds of functions are what we call periodic. And it's the first kind of periodic function we've studied all year. And what makes something periodic is that it repeats itself over and over. Okay, so I'm going to draw it out in a second by hand. And you're going to see that the y values start to repeat after a certain point. So let me go like this. Okay, so what I'm going to do is I'm going to take what we call one section of that blue graph. I'm going to trace it, and then take a look at it. So it starts here, goes up, goes down, and ends right there. Let's take that section and look at it. What do we have right there? That's called one cycle of the graph. Okay? It's not really called a section, it's a cycle. And the idea is, once you draw one cycle, you could take that one cycle, you could copy and paste it as many times as you need to, and that would be the second cycle. If I put another one, that would be the third cycle. Okay? It's that one cycle repeated over and over. So let's just focus back on one cycle. And if you look at the y values, they start at 0. And the highest they ever get, it's easier to see on this graph up here, is 1. So 0, 1, 0, negative 1, and back to 0. And then it'll go 1, 0, negative 1, 0, 1, 0, negative 1, 0. That 1, 0, negative 1, 0 pattern, that's what keeps repeating over and over. And it repeats after you travel this far. If you measure the length of that, what I just drew in blue, that's how far you have to travel before it repeats. If you don't travel that far, you haven't done a full cycle. If you travel beyond what I just drew, now you're drawing the next cycle. Anybody have an idea how far it is from here to there? I mean, it looks like it's, if you count, it's 5 tick marks, but each tick mark is not 1. So think about on the unit, like unit circle. How many degrees would you have to go through before you start tracing over the circle again? Yep.
360.
360 degrees, yep.
So is it a radian line?
Or what's 360 degrees in radians? Yep.
2 pi.
2 pi, yep. That's exactly what the distance is between these 2 points. 2 pi. That's the length of a cycle. And that's the next thing to write down. So the length that you have to travel before the graph starts to repeat itself is 2 pi units. So if I wanted to show you exactly one cycle on this graph, I could have it start at 0. And where do you think I would have it end? So it only shows one cycle. Well, how long did we just say a cycle is? 2 pi. So if you start at 0 and you travel one cycle, where would you end up? If you're traveling from 0 to the right one cycle.
It's 2 times
Or you could just tell me what, you don't actually have to do that out.
pi. 6.2.
Yeah, which is what? How did you get that?
I multiplied 2 with pi.
Yeah, it's just 2 pi. So if
Oh,
you,
you can just set it as that?
yeah.
Oh, I didn't
And then
know
when
that.
you press off it, it'll figure it out.
Oh.
Yeah, you can put calculations in there. Like you could do 5 times 2 and it would put in 10.
I didn't know that.
So if you start at 0 and you end at 2 pi, what you're going to see now is just one full cycle. Well, and the red one, but I'm focusing on the blue one. That, the red one, that is one cycle of cosine. But for now, just focus on the blue. Okay. If I wanted to show 2 full cycles, what do you think I would set my x max to? Instead of 2 pi, yep, 4 pi. If you set it from 0 to 4 pi, you'll see one cycle, and there's your second cycle. That's 2 cycles. I could show as many cycles as I want, but the idea is we usually just show one cycle. So whether I use the word cycle or period, they mean the same thing. If I ask you how long is one cycle of this graph, you'd say 2 pi. If I said what's the length of the period of the graph, 2 pi. It's the same thing. Sometimes you see the word cycle used more in, it's definitely used in electronics. Like if you know what hertz means. Does anybody know what that stands for? Yeah?
Is it just how many times it's refreshed a second?
Yeah, this is cycles per second. Right? And it's used different ways if you're talking about electricity. Alternating current, not your car, but like your house. The current in the US runs at 60 hertz. That's 60 cycles alternating current per second. Other countries use 50 hertz. So that's why if you have something that's designed to only work in 60 hertz and you plug it in another country that uses 50 hertz, it's not going to work well. It'll never work again. It'll probably destroy it. So you have to make sure, even if the device like physically fits in the outlet, it has to more than physically fit. It has to be the right kind of electricity. That's why if you look at like a lot of your transformers, when you plug them in, and they have all that really, really small writing on them, a lot of them say 50/60 hertz. So they work on both. But if you have something that doesn't say that, then you have to be careful plugging it in another country. We use the word period more in this class, but other subjects, other fields might use the word cycles.
Has that happened to you personally?
No, I've never. I usually make sure I know what I'm plugging in.
Yeah, you just seem very.
I don't want to have to try to replace something in another country if it's something I really need.
Yeah.
That could be challenging. But yeah, it's just something you have to be careful. Like generators, if you have a generator in your house, sometimes if it's kind of a cheaper generator, it might not be exactly 60, might be like 59.5 or something, which is pretty close, and it's probably going to work okay. If you had something that was like really sensitive electronics, you probably want to have a generator that's a real good one. It's got like an inverter built in, so that means you get the exact 60 hertz. But a lot of equipment, 59.5 is okay. It's not that far, but 50 is way too far off. That would ruin something. That's not made to run at that. Right, so when we are graphing sine or cosine, because they curve, you really need about 5 points. The beginning, the end, the middle, the high, the low. That's 5 points. And when we do a sketch, we are generally only going to sketch one cycle. Because if you can sketch one cycle, you could sketch 2 cycles. Just copy and paste the first one. And we said earlier that the entire length of a cycle is from 0 to 2 pi. That's 0 to 360. So this is the first quarter of your cycle. Second quarter. Third quarter. Fourth quarter. Because you're separating your cycle into quarters when you do that. 5 points separates something into 4 sections. Kind of like, if you have a string and you make one cut makes 2 pieces. So think of like these points, each one of those points separates it into a different section. These sections are all 90 degrees apart. The blue section is 0 to 90, the red is 90 to 180, the green is the 180 to 270, and the purple is 270 to 360, the last quarter. You can pick more points, but 5 is really what you need. Gives you nice points equally spaced at each quarter. Okay, so I call these like the 5 key points, or the 5 important coordinates that you need. And when we're graphing, you saw sine and cosine. They don't look exactly the same. So if I put cosine back in, and you might notice I'm not going to do it right now, but when I press zoom, I'm going to use zoom 7 a lot. Okay, so normally zoom 6 is what we use, but zoom 7 is what we use when we do trig. And it says trig right on it. Okay, so zoom 7 is, you'll see me use it. So if you look at sine, your 5 key points are 1, 2, 3, 4, 5. For cosine, they're different. 1, 2, 3, 4, 5. So what we want to do is make a table of the 5 key points that you can see in that picture. The x values we are going to do in radians. 0, pi over 2, pi, 3 pi over 2, 2 pi. Those numbers I just said correspond to 0, 90, 180, 270, 360. Okay, so let's start with sine. If we get these original tables wrong that we're about to write down, then every transformation that we do is going to be wrong. So these original tables give you the starting point. And then what we'll do with these original tables is either shift, stretch, or reflect. Those are the 3 things we always do with transformations. So let's look at sine. Okay, so look at the blue one. When x is 0, what's the y value? For the blue one, yeah? 0, yeah, 0, 0. The graph of sine goes right through the origin. Okay, so we've got 0, 0. Again, don't worry about cosine. We'll do that one in a minute. Let's just look at sine. Okay. How about the next one? When x is pi over 2, that's your first quarter point on the blue one. What's the y value there?
1.
What is it?
1.
1. Yep. When x is pi over 2, you're at 1. Okay. Now let's look at the halfway point. It's right in the middle of the blue graph. That's when x is pi. What's the y value when x is pi? Yep.
0.
Yep, 0. So you're halfway. Okay. The next x value is 3 pi over 2. So that's the 3/4 mark. What's the y value when we're 3/4 of the way through the first cycle on the blue graph? Yeah, -1. And then the last point, that's a repeat of the first point. That's the 2 pi mark. And what's the y value when we get to the end of the cycle? Yeah, 0. We're back at the beginning. So those are the 5 points that you want to know when you're doing a transformation of sine. Those are the first 5 points that will help you make a good sketch of the first cycle. Okay, now let's look at cosine. Same x values, because we want to keep them equally spaced. 0, 90, 180, 270, 360. So these are all the points at each quarter of the cycle. But now we're looking at the graph in red. What's the y value for the graph in red when x is 0? Yeah, 1. Okay, so we're starting out at 1. And then the pattern is basically just going to pick up from this number and just keep going. So when we get to pi over 2, that's the first quarter point on the red graph. What's my y value when x is pi over 2 on the red one? Yeah.
0.
Yep, we're at 0. And then my next y value, when we're at pi, will be at yep, -1. 3 pi over 2 on the red one, we're going to be back at 0. And then 2 pi is where we end on the red one. And where do we end? 1. We end at 1. So those are the 5 points that will help you sketch the first cycle of a cosine graph. And the tables are different. The x's aren't, but the y's are. So we have to make sure we use the right table. Any questions on either of where these points are coming from looking at that graph? So what we're going to do for today is we're only going to do an individual transformation, single. So for example, shift left, and that's it. Not a shift left and then a stretch, just shift left, or just shift right. Okay, we're only going to do one transformation at a time for today. So what that means is if we're only doing one transformation, in those tables I gave you, only one column is going to change. Think about if you shift up. If you take a coordinate and shift up, what part of the coordinate doesn't change? Yeah,
The x.
the x. Shifting up or down doesn't change the x. It only changes the y. So the x would change, the y would stay the same. If you shift left or right, well, that's different. Shifting left or right, the x is going to change. And the y would stay the same. Okay, so for all the problems that we do today, one stays the same, the other column will change. Okay, so that's kind of the background about sine and cosine. Next, we'll go through each transformation one at a time. Okay, starting with a phase shift. We normally we haven't seen that word before, phase shift. But a phase shift is when you shift the graph left or right. Why don't they call it a horizontal shift? I don't know. With sine and cosine and all the trig functions, they call it a phase shift. But it just means horizontal shift. Now, think about when we've done horizontal shifts before. There's two kinds of arithmetic that are involved. You either have adding and subtracting, or you have multiplying. Shifting uses what kind of arithmetic? Yeah.
Adding, subtracting.
It's always adding and subtracting. The difference is either left and right or up and down. Right? But shifting is always adding or subtracting. And when it's horizontal, is it inside or outside? Yep.
Inside. Right?
Inside. Yep. So by inside, we mean what you're adding or subtracting is in the parentheses. If you put it on the end of the function, that's different. That's outside. Okay, so inside means in the parentheses. And just like all horizontal transformations, it is backwards. So if you add, it's going to shift the graph which way? Left. So when you add, it's actually moving left, which means all the x's are moving towards the negative direction. Like they're getting smaller. How about when you subtract? Yep.
It goes right.
It's going to shift it to the right, which means if x's are moving to the right, the x values are actually getting bigger. Okay, so that's just something we have to remember. Adding moves it left. Let me just write it down. Bless you.
Is there a particular reason why it's like that? Just because.
Why it moves it that way?
Yeah. Is it just because of how the math looks up?
Yeah, I can show you after if you want to see. But yeah. Okay, so adding moves left, minus moves it right. Oh, I wrote that down anyway. Never mind. So x minus moves right, x plus moves it left. That's what I just summarized right here. And how much does it move? Well, it moves that much, whatever that number is. Technically, you can move it left to right any amount you want. But the most common amounts that we're going to move it are either 90 degrees, 180, or 45. Those are the most common. You could shift it right by 13 degrees if you wanted. That's not very common. Okay, so if we're going to be shifting left and right, think of those original tables. What values are affected when you start moving things left and right? Yeah.
The x values.
Right, the x values are going to be affected. The y values are not. So we are not going to have to change any of our y values. So what are we going to do? We're going to copy them down from the original table. The way this kind of problem is graded is you have the original table. I need you to figure out the new table. The new table is the table you get after you shift it left or right. The new table is going to look like this. It's going to have 5 x's. It's going to have 5 y's. You get 1 point for each x and y value you get right. So that means the table is 10 points. And out of the sketch, the table is the most important part. Okay, that's worth 10 of the points in the problem. The sketch itself, that's usually just worth a couple points. Because once you have the table, the sketch is just plotting the points in the table. But you got to get the table right. Okay, so y's stay the same. All the x's are going to change. So let's kind of look at our first example. First example is going to have an x minus pi over 2. Which way is that graph going to go? Because it's minus pi over 2. Yeah?
Right.
Everything's going to go to the right. What really happens to x values if they're moving to the right? They're getting... What's happening to them? Yeah?
They're getting bigger.
They're getting bigger, yes. So what's going to happen to all the x values in this problem? They're all going to get bigger. How much bigger? That much bigger. Every x value is going to have something added to it. So that's why when I write step 2, I say to look at what's been added or subtracted. In this case, we're subtracting pi over 2. But we know they all have to move to the right. Well, the only way they can move to the right is if you add something to them. So you always have to do the opposite. Now, the only annoying thing is we are going to be working with fractions, and they're all going to have pi in them. So generally, a calculator isn't really going to help. We're gonna leave everything as pi's. Right? We're not gonna put down decimals. Okay. Does everyone have what they need for steps 1 and 2? So now let's try to graph example 1. Okay, first step, are we doing a sine or a cosine problem?
Sine.
Sine. So we have to make sure we start with the table that was here, table for sine. So I'm going to copy that so I have it, so I don't have to keep going back to it. Okay. I'm going to put the original values, well, let's actually write down the values that don't change. Okay. This is a phase shift, because you're adding and subtracting inside the parentheses. What values in this table are not going to be affected? Yeah?
Why?
The y's. So let's write down the y's from the original table. What are my y values for sine? Yeah.
0, 1, 0, negative 1, 0.
Yep. Okay, so if you get that right, there's 5 points right there. Just knowing those. 0, 1, 0, negative 1, 0. All my final answers are going to be in the table that I just put a box around, right there. What are my original x values for sine? I'm just going to put them off to the side. Yep.
0, pi over 2, pi, 3 pi over 2, 2 pi.
Yep. And remember, these aren't just random numbers. These are all numbers that are nicely spaced. 0, 90, 180, 270, 360 in degrees. Okay. Now, are we going to add or are we going to subtract from all of those? Add. Yep, we're going to add because everything is supposed to move to the right. And how much are you going to add to all of them?
Pi 2.
Pi over 2. So we're taking every x value, we're taking them all together, and they're all shifting to the right the same amount. Okay, so first one, that's relatively straightforward. 0 plus pi over 2 is pi over 2. Next one already has a common denominator. What's pi over 2 plus pi over 2?
Would it be 5?
Yeah, it would be 2 pi over 2, which is pi. Yep. Okay, next one, we don't have a common denominator. Pi plus pi over 2.
3 pi over 2.
What What would be, yeah, it will be 3 pi over 2. But just in case anyone doesn't see that, what's your common denominator between 1 and 2? 2. So times 2 times 2. Now you have 2 pi over 2 plus 1 pi over 2, which is 3 pi over 2. Okay. Next one already has a common denominator. It's 3 pi over 2 plus 1 pi over 2. Yep. 2 pi. I'm going to write it as 4 pi over 2 and then simplify it to 2 pi, because I want you to see a pattern in a second. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. If we were going to do another cycle, it would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. And yes, some of those reduce, like 6 pi over 2, like that. That's it. That's your table. Any questions on how we added pi over 2 to all the originals to get all the new ones? Okay. So now let's graph it. These are the values we started with. Are these values all equally spaced, the ones we started with? Yeah. We shifted every one of them together exactly the same amount. So are these values equally spaced? What do you think? Caleb?
Yeah.
Yeah, they're still equally spaced. This is 90, 180, 270, 360, 450. Just plus 90 each time. We're just starting at a higher value. So when we label our axes, the only rule when you label axes is that you keep everything equally spaced. So let's use these as our labels. This would be 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. You do have to put those labels in. Okay, if you don't, then I'm going to assume 0, 1, 2, 3, 4, 5. And that's not what these numbers are. Up and down, what's the highest y value we need? 1. And the lowest? Negative 1. So because I am going to go by 1s on my y-axis, you technically don't have to label the y's. Because anytime you don't label tick marks, I'm going to assume 1. Okay, now graph your points. So pi over 2, you're at 0. Pi, you're at 1. 3 pi over 2, 0. 2 pi, you are at negative 1. And 5 pi over 2, back at 0. And try to make the graph look curved. There's nothing sharp about these graphs. They're all like smooth curve. So this is the new one. And if you wanted to see what the original looked like, it would have been here, 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 and there. I'm just showing you the original for reference. So the graph in purple slid to the right 1 tint mark, which is 90 degrees to the right. Okay, and that's called a phase shift. Okay, any questions on that? And there's no reason to draw a second cycle, because if we can do 1 cycle, we could do 10 cycles. You just have to continue the pattern like I was doing. 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, and then continue the pattern with the y's. 1, 0, negative 1, 0. 1, 0, negative 1, 0. As many times as you want. Yeah.
Would you like us to put the original?
I think on the homework tonight there's 2 graphs. I think the left side says original, and the right side says new. So you'll be doing them as separate graphs. I did them on the same graph just because it's easier to see the difference. But for the table, once you do the original table in the homework for sine, and then you do the original table once for cosine, you don't have to keep writing it down. I would just put this like at the top of your notes and then just look at it every time you need to do a problem. If it helps you to write it every time, you can. Probably memorize it that way, but it's up to you. Okay, let's look at this one. Okay, so first thing, once we know more transformations, is we got to figure out which one this is. This one's a phase shift, but can anybody tell me why it's a phase shift? Yeah.
It's adding pi in parentheses.
Right, two things that make it a phase shift. It's addition, inside. Yep. Addition makes it a shift. Inside makes it horizontal.
So if it's outside, that means vertical?
Yep, outside, I don't know if we're going to do that one today, but if you had this, that's up 3. Yep. Maybe we do that one today, I don't remember. Yeah, we do. That's the last one. Okay, so this is shifting horizontal, left and right. Which column is going to remain unchanged? Yep. Y's. And can you tell me what my y's are for cosine?
1, 0, negative 1, 0. 1.
Okay, 1, 0, negative 1, 0, 1. I'm going to put all our answers in that table. Can someone remind me the original x values for cosine? And I'm not going to put them in the table. I'm just going to put them on the outside because I have work to do on them. Yep.
0, pi over 2, pi, 3 pi over 2, 2 pi.
Okay, and what, we're going to add or are we going to subtract to all of those? Yep, we're going to subtract, and how much? We're going to subtract pi. Okay, so subtract pi from all of them, and then that'll be your new x's. Okay, so the first one, 0 minus pi is negative pi. How about pi over 2 minus pi? What's your common denominator there? 2. So times 2 times 2. So what's 1 pi over 2? Take away 2 pi over 2.
Negative pi over 2.
Yep, negative pi over 2. And the next x value, pi minus pi, 0. The next one is 3 pi over 2 minus pi. Well, it's the same as the one we just did off to the side, except just put a 3 right there. So what's
Pi over 2.
pi over 2? And what about 2 pi take away pi? Pi. Now, you might not see a pattern here because they don't all have the same denominator, but this is negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2. Just keep going. But we always reduce what we can so that way it's simplified. Okay, any questions on the table? All right, so now let's do our graph. Again, highest and lowest is 1 and negative 1. And we have to go from negative pi to positive pi. So we need 2 values in the negative direction, so I would put negative pi right there. Then negative pi over 2. don't have to label 0. I mean, I know 0 has to be the axis. You can't change that. And then pi over 2 and pi. So in degrees, these are the numbers negative 180, negative 90, 0, 90, 180. They're all 90 apart. Okay, and now let me just zoom out and do my sketch. So negative pi, we're at 1, 0, negative 1, 0, 1. Now, that kind of looks like a V shape. Don't draw it as a V though. Remember, it looks like that. You're sketching that. You're not sketching that. Right? There's no sharp turn in any of these graphs. So just try to make it look a little bit curved. The idea is if you copy and pasted that, it would look like a wave continuing. Just do there. And that's it. Any question on that? Okay, so again, most important thing I'm looking for, the table. That's going to be set up in pair assessment. It'll be an actual table. You'll click in each cell, and then you'll just type in all 10 of those numbers. Let's try this one. So this will be our last horizontal, and then we'll finish with vertical. Okay. So one more time, which column stays the same? Yep, y column stays the same. And what are my y's for sine? Yep.
0, 1, 0, negative 1, 0.
Okay, so I got my original y's, which are the same as my final. They're not changing. Now I need my original x's, but I'm going to put them off to the side because they're all going to change. What are my original x values? They're just all the x's that are spaced every 90. But in radians. Yep.
0, pi over 2, pi, 3 pi over 2, and 2 pi.
Okay, and all of those need to be adjusted. And what are we going to do to every one of them? How about Lewis? What do you think we're going to do to all those?
0 would be just negative pi over 4.
And how did you get that? What did you do to it?
You subtract.
Yeah, we're going to subtract pi over 4 from all of them. So the first one, what you said was right, negative pi over 4. Now let's do pi over 2. What's the common denominator between 2 and 4? Yep, 4. And what would you multiply by to make the bottom a 4?
2.
2. Times 2 times 2. Okay. What's 2 pi over 4? Take away 1 pi over 4. Yeah.
1 pi over 4.
1 pi over 4. Let's do one more, and then I think we'll see the pattern, and then we can just copy the pattern for the rest. Pi minus pi over 4. What's the denominator on the pi right now? Because there isn't one.
1.
Yeah, it's a 1. Common denominator between 1 and 4? 4. Times 4 times 4. What's 4 pi over 4 minus 1 pi over 4? 3 pi over 4. And so we have negative 1, 1, 3. What do you think the next number in the top is?
5.
5. And the next one? 7. And if we had to keep going, then it would be 9 pi over 4, 11 pi over 4, 13, 15, 17. That's the pattern. Okay. Any question on that one? Okay. Now, let's, for a second, just focus on these numbers in front. -1, 1, 3, 5, 7. Let's imagine you were putting those numbers on a number line. Okay. Here's 0. Here's -1. Okay. Where would 1 go? Yeah.
Next to the 0 on the right.
Right next to 0 on the right. Now, where would 3 go?
Space over.
We have to skip a space. You can't put 3 there because that's 2. That's 5. That's 7. 0 is usually always labeled because it's the axis, but we're not actually using 0. 0 isn't in this table at all. So our points would really be, if I was just graphing those 5 points on a number line. Okay? Now we're going to do the same thing, except with pi over 4. So we're going to remember that we have to skip. Okay? So when we set up our graph, this is negative pi over 4. This is 0 pi over 4. That's 1 pi over 4. This is 2 pi over 4. We don't need it. We need 3 pi over 4. We don't need 4 pi over 4, but we need 5 pi over 4. Did we need 7 pi over 4? Oh, we did. So I didn't make this long enough. Okay, so any question on why I skipped there? If it gets confusing, just think of it without the pi over 4. -1, 0, 1. That's a 3, not a 2. So it skips 2. Okay, and the highest, lowest, and there's your graph. Okay, so we've got negative pi over 4, we're at 0. 1, 0, -1. Just make sure I did everything right. I think that looks good. It's a little messed up at the end because I didn't use graph like straight lines to draw it, but it's okay. Okay, any questions on that? And that's a small shift. Okay, pi over 4, that's 45 degrees. That's the smallest one we did. So it's just a little bit of a shift to the left. Not much. All right, so out of the two we're looking at today, that's the harder one because you have to deal with the pi and the common denominator. Shifting up and down is very easy because all we have to do when we shift up and down is deal with a 1, a -1, or a 0. Those are very easy to do arithmetic with. So remind me again, what operations shift functions? Either, yep, right. It's going to be either adding or subtracting, but this time it's on the outside. So it's plus or minus, but it's a number on the end. And when we're shifting up and down, we usually shift by a nice number. 1 unit, 2 units, 3 units, 5 units. Which way would add move the graph when we're talking about vertical shifts? Yep. Up. And subtract? Down. It's not backwards. Vertical is never backwards. Just like we've done that all year. Add is up. Subtract is down. All right. So now we know what we're looking for when we see a vertical shift, adding or subtracting on the outside. Technically, it doesn't have to be at the end. That is exactly the same as this. There's no difference. 3 plus 2, 2 plus 3. You can switch the order when you add. But I usually like to put it at the end. What is not going to be affected when you move something up and down? The x. So all the x's are going to stay the same. That means for every shift we do up and down today, the x's are 0, pi over 2, pi, 3 pi over 2, 2 pi. They don't change. Well, if the x's are going to stay the same, then the y's are going to change. The y values are going to be, we either add or subtract to the originals. But don't do the opposite. If you see a plus 3, do a plus 3 to all the y's. If you see a minus 5, do a minus 5. Don't do the opposite if you want to get it right. Okay. So let's look at this cosine graph. How do we know that this is a vertical shift and not horizontal? Yep.
It's not in parentheses.
Right, it's not, it has to be grouped with the x. That's horizontal now. That's kind of a weird amount horizontal. We don't usually shift by 2. But there's no parentheses there, right? That makes it a vertical. So what column is going to stay the same? Yep, and can you tell me my x's for cosine?
Zero. Pi over 2. Pi. 3 pi over 2.
2 pi. Okay, so we've got our x's. Let's put the original y's on the outside. What are my y values for cosine? Just the original. Yeah. Yeah, original.
1, 0, 1, 0.
Okay. And now we've got the originals, and what are we going to do to all 5 of them? Yeah.
Add 2.
Add 2. So when I add 2 to all of them, can anybody give me all my new y values? Yep.
3, 2, 1, 2.
Yep. 3, 2, 1, 2, 3. And that's it. So the arithmetic, I think, is easier with a vertical shift than it is with a horizontal. Okay, so the highest you need to go is 3. So let's number it 0 to 3. Because I know my graph is going to be shifted up, I'm going to put my labels down here so I don't draw over them. If the graph had been shifted down, then I probably would have put the labels above so they'd be out of the way. Okay, so we have 3, 2, 1, 2, 3. So this is the cosine function. It looks like the middle part, which is like that V shape, but just try to make it look curved. Like that. Okay, so that's a cosine function shifted up to. Any questions on that one? All right, so let's finish up with a sine function shifted down 3. Okay, so Nick, what column is going to stay the same?
Yes.
Yep, and can you remind me what my x's are for sine?
Was it 0, pi over 2, pi, 3 pi over 2, and 2 pi?
Yep. Okay, now I need the original y's. What are the y values for sine? Just the original. Caleb?
0, 1, 0, 0.
Yep. 0, 1, 0, negative 1, 0. And what are we going to do to all 5 of them? Yep. We're going to subtract 3. So we're going to get negative 3, 1 minus 3, 0 minus 3, negative 1 minus 3, and 0 minus 3. So we need to go down to negative 4, and the highest we ever go is negative 2. So I'm going to go by ones. That should be fine. I am going to put my labels above this time because I know the graph is going to be below. So 0, pi over 2 pi. So 0, negative 3. Pi over 2, negative 2. Negative 3. Negative 4. And negative 3. So it's the sine function, and it's been brought down 3 units. That's it. Any question on that? All right, perfect. So the homework for tonight is to graph those 7. There is a worksheet online. If you click on it, and it has the graph paper already on it, if you want to use it. And those 7 problems are already written on the worksheet in the homework as well.
Do you have graph paper in here?
There is some graph paper, I think, under the TV in the back.
I just have an extra.
Who wants?
Okay, so what I said earlier, there is no worksheet for this one. You're just going to do those 7 problems. So make sure you copy those down. There is no worksheet.